Good morning, class. Welcome to the online classes for class 11th. In the previous classes, we were learning about the chapter motion in plane. In that, we have seen what the projectile motion is. So, here in the motion in plane, we will be seeing the new motion, which is a circular motion. If you want to see in the book, you can see it as a uniform circular motion. You will get the topic. So, what this circular motion is? Now we know that whenever a body starts moving or a moving object is said to possess motion, right? So when we say that a moving object is there, then we say that the body is in a motion. So this is a circular motion. So here also the body is moving, but the motion of that body or a particle is maybe moving in a circular form or complete circle, right? It is moving around a complete circle. But if we talk about the circular motion, then if a particle moves along a circular path, that is, the path should be in the form of a circle, and it moves around the boundaries of the circle. So we can say that if the motion of a particle is around the circle or on the path of the circular form, then it is said to be the circular motion. Okay, so we can say that not necessary that the motion should be throughout the circle or a starting point should come to the end point of the circle. It can be on the part of a circle also, that is the arc of the circle can also be said. So the motion on the arc of the circle can also be said as the circular motion. Like this is a circle. If you start from here and you cover the whole throughout the circle, then it is said to be circular motion. This is also a circular motion, and if you are just moving from here to here, this is an arc, right? If you point it as A and B, then from A to B is also in the form of a circle, right? When we move, we have to change the velocity and we are changing the direction also. So this kind of motion in the part of a circle or through the arc of a circle or around the complete circle is said to be the circular motion. So in which, if we want to see that it is uniform circular motion, then you can just understand that circular motion along a circular path, if it moves in a constant speed, that it covers a equal distance and equal interval of time, then it is said to be the uniform circular motion. So equal distances covered in equal interval of time is said to be the uniform motion. So if it is circular motion, then we can say that it is covering the equal distances along the circumference of the circle, because we know that whenever a body is moving, then it is moving along the circumference of the circle, right, on the path of the circle. So this is said to be that whenever a body starts moving around the circumference of the circle in equal interval of time, then it is said to be the uniform circular motion. So we can say that for it is not necessary the body should complete whole full circle, but if it moves along the arc also, then it is said to be the circular motion, right? So here we will go through the motion chapter, which we read in the 9th class also. Once recall it that you have learned what the motion includes, what are the words that included in the motion, that what the body covers the distance, what was the displacement, and if it covers the displacement with respect to the time, it is said to be the velocity, which is the vector quantity, and when it depends on the scalar, then it is speed. And after that we have seen what velocity is, and velocity changes with respect to the time, that is said to be the acceleration. Same here, for that it was a linear motion that you have studied in the motion in straight line also. Similarly, you will be studying for the circular motion also, but the name will be changing. Like for displacement or for completing the distance, it will be said to be the angular displacement, and angular velocity will come, and the angular acceleration will be coming. So here every word will be converted into the angular, that is, when we move into the circular form or complete the circumference of the circle, then we are just maintaining an angle towards the center, that is theta, towards the center of the circle. Okay. So here are the examples through which we can see the circular motion, that is an orbit. In an orbit, the planets revolve around the sun. We can say that the path is not a particular circle, but it is an elliptical orbit. We know that Kepler already told that path of the planets revolve around the sun is not a particular circle form, it is an elliptical orbit, but then also they are traveling in the arc form, so we can say that it is a circular motion. And similarly, the moon revolving around the earth, or the second example you can see here, the giant wheel, or in a circular orbit, if we run also, if we jogging also, or cycling to be done in the circular tracks, everything which are moving around in the circular tracks or in the circular form, even we can say that is in the part of an arc also, is said to be the circular motion. So why we use the circular motion? It is more helpful in understanding about the motion of planets because it is a form of a circle. So we can say it is useful in the motion of planets to understand the motion of the electrons around the nucleus, because electrons also move in the form of orbit that is around the nucleus. Orbit formed around the nucleus are in the form of a circle. So there also the electrons are moving and having a circular motion. Similarly, motion of a giant wheel, motion of space stations that are moving around the earth due to the gravitational orbits of the earth, and the motion of moon and satellites around the earth due to the gravitation of earth. So these are the reasons why we used to study and give the formulas for the circular motion, right? So after this you can see this in the book also, so you can refer to the book also. Firstly understand, then you can see your book. Okay, we will relate the linear as well as the angular velocities, accelerations and displacements. But before going to angular velocities and displacement, you will see whenever a body moves in the circular region, that is if there is a circle, then we can say this part is also a circular motion, right? Small element, we are just considering a small element, that if we moving from the point A to point B, then also we are considering that we are moving in a circular form. So this is also a part of circular motion. Now let us consider that we are moving del s, that is the displacement of the body in this arc bs, but we are taking the elementary, that is a small displacement by the particle, is the area or the angle stepped out by that particle can be given as del s, that is the displacement of that particle in that arc. Now we see that if there is an arc, then towards the center it will make an angle, that is theta. Okay, so this displacement can be said that it is in the linear form, right? Because linear form it can be in the arc also, but if you take the throughout the arc the particle that is from A to B, then we can say that it is towards the center, an angle is made, so it is moving with an angular, right? It is angle stepped out by the radius is said to be the displacement. So here in the previous classes we have seen that displacement is given by s. So in this arc we given that the change in the displacement is given by del s, that is a distance covered by a particle from point A to point B. So distance covered by the particle A to B is given by del s, and this distance will be with respect to the radius, right? Radius of the circle. And we know that if we divide, or the ratio of these positions of the object moving from A to B and the radius of the circle is given by r, then this ratio is said to be the angular displacement. And what the displacement will be given by, since it is forming a displace through an angle towards the center, then it is given by the value theta. So theta is equals to del s upon del r, but we are taking a small element, so we can write it as del theta is equals to del s upon del r. So this is the first formula for the angular displacement. So angular displacement is given with the letter denoted by the letter theta. It is given by the angular displacement is given by the linear displacement upon the radius r. So we can say that angular displacement is given by the angle, that is theta, and it is shown that if we move from a point A to B in an arc form, then the displaced body position is given by del s and the radius is given r. So we can say that it makes an angle theta with the center. So angular displacement theta is given as del s upon del r. Now if we want to know about the unit of this displacement, then it is given by, since we have seen that arc, that is the displacement covered by the arc from A to B, so it is given as arc. Okay, and the second one r was given by the radius, so we can write it as radius. So arc upon radius is the formula for the angle, but to write the angle's value we take it as radian. You can also say that the degree is also there for theta, because we use in maths that 90 degrees, 60 degree, 50 degree, for degree is also used, but we can convert this degree into radian also, and radian can also be converted into degree. So here we are just taking the small elementary particle that is moving from A to B and covering a distance s towards the center with making an angle theta. So it is given by radian. Okay, so the angular displacement unit is radian. So if we just differentiate between the linear displacement and angular displacement, then you can see that linear displacement is given by s and angular displacement is given by theta. And for displacement s, we just measure this in the form of meter, that is meter is given or centimeter is also used, while for theta it is used as radian. So this is the simple differentiate between the linear displacement and the angular displacement. After displacement we go through the speed and the velocity, but here we will be seeing only the velocity, that is the vector quantity. So we know that velocity is always the displacement upon time, right? Displacement upon, that is s or d, you can say distance or the displacement upon time, that is the total distance covered or the displaced body upon the time taken by the body to displace. This is the ratio of the displacement and time is given by the velocity. But we are taking a circular motion, that is a body moving in the circular form. So here we can say that the time changed, rate of time of change to cover a distance but in an angular form. So the angular displacement of particle, if it is divided by time t, that is theta upon t. So this is the angular displacement upon time, because the velocity is defined as a displacement per unit time. So here the angular displacement per unit time is given as the angular velocity, okay, theta upon t. And if you take a small elementary particles than instant average velocity, then it is given as del theta upon del t, okay. So the angular velocity is the rate of change of angular displacement of the particle with respect to the time is said to be the angular velocity. So angular velocity is denoted by the letter omega, that is omega. It is similar to that of W itself. So it is omega, and omega is given by del theta upon del t or theta upon t. Simply we can say that the rate of change of angular displacement with respect to the time, theta upon t. And for the unit of the velocity, we know that linear velocity is given by meter per second, that is displacement is covered in meter and time is covered with seconds, so it was given by meter per second. So for theta upon t we can write it as radian for theta, and for time it is given as seconds. So we can say this as radian per second. So omega, that is the angular velocity, is unit, or it is measured in the form of radian per second, okay. So what is the difference between the linear velocity and the angular velocity? That is, linear velocity was given by v, it was change in the displacement upon the time taken. Here the angular velocity is given by omega, that is angular displacement upon time, right? For this we use meter per second, that is linear velocity is measured in meter per second and the angular velocity is measured in the radian per second. Similar to that, but meter was taken for the linear straight line motion, but in the circular motion we are taking an arc, that is angle subtended by the center, so it will be taken as radian. So it is radian per second. This is the angular velocity and angular displacement, right? After that you can see what the time, because in that we have used t, that is t seconds, that is time taken by the body to cover that distance. But here the time taken by the particle that revolving around the circle can be said as, that is, if it is completing the whole circle, the motion is said to be circular motion. So we can say that the body is displacing from a single point to come back to that point, is said that the time taken by the body to cover this distance is said to be the time period. So time is just to cover a distance, right? And if it is time period, that is given by the capital T. So this is the difference between time and the time period. Time is given by small t and time period is given by capital T. So we can say time small t is just the time taken by the body to cover the distance, but time period is the time taken by the particle to complete that whole, you can say the whole revolutions or whole rotation or the whole displacement. So the together the time taken by the body is said to be the time period. It is given by the capital letter T. So the time period is the time taken by the particle to complete one revolution around this circular track. So one revolution, you can say the time taken by you to complete a circular track is said to be the time period, capital T. Here also it is measured in the second, because time period or the time will be measured in the seconds and hours also, okay. So after that, since it is moving in a circular track, so the body is revolving, so we can say that the time taken by the body to revolve is given by time period. And if this body is per second, if it is completing some revolution, then we will be using frequency, and I think you are familiar with this words also. Frequency is given by the number of revolutions per second, right? And the easy words, you can say number of revolutions per second, number of oscillations per second, or the number of vibrations per second, because this, I think you have remembered, you have seen for the wave also, that for 1 second how many waves can travel, right? So that was number of vibrations or the number of oscillations per second, but here the number of revolutions per second, because it is revolving around a circle, so we can say that the number of revolutions per second. So in 1 second, how the object can move, or the number of the revolutions completed by that object in 1 second, is said to be the frequency. It is given by the letter nu. It is nu. Okay, small bend will be there in the v. It is nu equals to time taken by the body, or the revolution taken by the body in 1 second. So it is 1 by t. So we can say that frequency is just inversely proportional to the time period, or time period is inversely proportional to the nu. That is, frequency and time period are inversely proportional to each other. Okay, we have read the velocity also. We have read the linear velocity, angular velocity, linear acceleration. Now we will see this acceleration, because velocity, displacement you have already read. Now we will see the acceleration. Okay, so for angular acceleration, before going to that, we know linear acceleration, acceleration a, it is denoted by the letter a, and it is equals to the displacement upon time was velocity, and the velocity upon time was given by acceleration. So velocity upon time, right? Velocity upon time. Acceleration was given by the change in the velocity upon time, because v minus u was also used. Okay, so that is del v upon del t. So here the a is replaced by alpha, that is the angular acceleration is given by the letter alpha, and it is equals to angular velocity upon the angular time, right? Time period upon the angular velocity, and this velocity can be changed in velocity can be given by d omega upon dt, or del omega upon del t. So this is the change in the angular velocity with respect to time is said to be the angular acceleration, and the angular acceleration is given by the letter alpha. Okay, so alpha is given by del omega upon del t. So differentiating on linear velocity and the angular velocity, we can say that angular acceleration and the linear acceleration, linear was given by a and the angular acceleration was given by alpha. A was equal to del v upon del t, that is the rate of change of velocity with respect to time. And similarly, the angular acceleration is given by the rate of the change of the angular velocity with respect to time. So if you want to relate this angular velocities, angular displacement, or the angular acceleration with the linear velocity and acceleration, so we will some derivations that how we use it. We know that the omega was given by change in the displacement with respect to time. We know that displacement upon time was given by velocity. For angular acceleration, it is given by the rate of change of angular displacement upon time. Okay, and time period will be taken as capital T, because we are revolving an object throughout the circular path. So here the T will be given as capital T. So time period will come. And for theta, this is the angular displacement, how much it just throughout the circle. So if we take a circle, then how much is displaced if it's starting from point A, and if it just move throughout the circle and come back to the point B. So it is one revolution, right? It completed one revolution, which will be equals to the 2 pi r. But it is not covering throughout the radius also, so we can write it as 2 pi. Okay, so for theta we are writing it as 2 pi r for the circumference, but radius we are not covering, we are just moving on the path of the circular track, so we can write it as 2 pi. R is negligible. Here the time period t is given as t, so omega will be equal to 2 pi upon capital T. Okay, from here again we can write this 1 by t as nu, right? Frequency was inversely proportional to time period, that is nu is equals to 1 by t, or 1 by t is equals to nu, that is t is equals to 1 by nu also. Any relation you can take it as, because both are inversely proportional to each other. So in with respect to 1 by t, we have written it as nu, so omega can be written as 2 pi nu. This are the formulas which will be useful in your numericals, that is omega equals to 2 pi nu. So this is the relation between the frequency and omega. Okay, that is angular velocity and frequency. In books you can see that as omega v and t, or omega nu and t, relation between omega nu and t. So omega is equals to 2 pi nu. Just remember this 2 pi by t and 2 pi nu. These are the important formulas you can say which will be useful for you. And after that, for angular acceleration, we will see the relation between the angular acceleration and the linear acceleration. Okay, now we have seen that v was equals to angular acceleration was given by angular displacement upon time, but for velocity we knew that it is linear displacement upon time. Okay, so from here we will be seeing what the alpha tells us about. Now alpha is equals to d omega upon dt, right? d omega is equals to, alpha is equals to d omega upon dt. Now we will be using this, but before this we should know the relation between the linear velocity and the linear angular velocity. So linear velocity was given by v, okay, and we know this velocity is given by the ds upon dt, right? Let this be the first equation, that v is equals to ds upon dt. And the second thing, we know that omega is given by d theta by dt. Omega is given by d theta by dt. Okay, d theta by dt is equals to omega, v is equals to ds by dt, that is rate of change of displacement with respect to time, and it is rate of change of angular displacement with respect to the time. These all are the instantaneous. Okay, remember that instantaneous is given by del and the average is given by d. So anything if you use, just remember what you are using the terms. D is given for the average one and del is given for the instantaneous one. Okay. So theta was given as s upon r, right? Theta was given by s upon r. Now for d theta by dt, what we can write it as d by dt of s upon r. So here what we can write, that ds upon dt, right? ds upon dt, and 1 by r will come out, right? So on differentiating this theta, we can write it as d theta by dt is equals to d theta by dt is equals to 1 upon r ds by dt or del s by dt. That for instantaneous it will be del s upon del t. Now we know this del s upon del t is equals to v, that is linear velocity v, so 1 by r into v, and d theta by dt, that is angular velocity, so we can write it as omega is equals to v by r. So omega is equals to v by r. This is the relation between the linear velocity and the angular velocity. Omega is equals to v by r, or we can write as v is equals to omega r. So this is the first relation. Before this we have seen that omega is equals to 2 pi nu or 2 pi by t. So these were the two formulas which we have seen now. Okay, v is equals to omega r and omega is equals to 2 pi nu or 2 pi by t. So now we will using this equation in the angular acceleration and linear acceleration also, because we have started but we don't know the relation between linear and angular velocity, so we didn't derive at that. Now if we see that alpha, we know that d omega upon dt, right? It is d omega upon dt, and we know that acceleration a was equals to dv by dt, and now only we have derived that v is equals to omega r, right? V is equals to omega r. So on putting this value of v omega r in acceleration, that is linear acceleration, a is equals to d omega, alpha is equals to d omega upon dt, but omega was equals to what? Omega was equals to, that is v, so v is equals to omega r, acceleration small a is equals to dv by dt. So instead of v, we will be using omega r d by dt, omega r. So here the r will come out because it is not, radius is not differentiated with respect to time. So we can write acceleration is equals to r d omega upon dt. So r is there and d omega by dt was given by alpha. So we can write this a is equals to alpha r or r into alpha. This is the relation between the linear acceleration or the angular acceleration. So a is equals to alpha r. This is the first relationship between the linear and the angular acceleration, and these three are the vector quantities. So it is given by the cross product, alpha cross r. Okay, so here these are the formulas which we have seen. That firstly we have seen that the linear displacement was given by s, right? S was a linear displacement. Linear displacement was given by s and the angular displacement was given by theta. Linear velocity was given by v and angular velocity is given by omega. Linear acceleration was given by a and angular acceleration is given by alpha. These were the terms which we used, and for velocity and displacement we used to give the measurement as meter and meter per second, and for the linear acceleration it was meter per second square. But in the angular we will be using different, that is one is radian, the other is radian per second, and the last one is radian per second square, right? You can just differentiate between these and you can remember, if you will compare together, then you can read it more better and can by heart easily. So after that we have learned about the relationships, and we have written that omega is equals to 2 pi by t or 2 pi nu, and the next one we have read, that is relationship between the linear velocity and the angular velocity, that is v is equals to omega r or omega is equals to v by r. This was the second relation. And the third, we have read the relationship between the linear acceleration and the angular acceleration, that is a is equals to alpha r, and this was given by the cross product because three of them are the vector quantities. So it is a is equals to alpha r. Okay, got it? That in circular motions we will be taking the each and every velocities, the displacement and the acceleration with regarding to the linear, we are changing it into the angular, right? And here are the formulas which you can see. This thing you can read in the book also, so I'm not relating to the book. If by seeing this video and you open your books before you can just understand what I'm telling about. And after this relations, you can just see the revision for your formulas which you will be using in the numericals. First was angular displacement, which was given by the displacement through the arc and between the radius, which was given by s upon r. Secondly, we have said that the displacement is given by theta, so the displacement upon time, it is angular displacement upon time, is given by the angular velocity, and it is denoted by the letter omega. So omega is equals to d theta by dt or theta upon t, that is time. That is time, not time period, and time period is given by capital T. It is the time taken by a body to complete the whole revolution throughout the circular path. Okay, and next we have seen the relationship between the v and nu and omega, that is omega is equals to 2 pi by t or omega is equals to 2 pi nu. And after that we have seen linear velocity, that is v is equals to omega r, and linear acceleration, that is a is equals to alpha r. Okay, and this centripetal acceleration and centripetal force I will be telling you in the next class, because this is a different topic which you should remember. In your book it is not given in the vast, because it is just given as a definition. So in the next class we will be seeing what the centripetal force and the centripetal acceleration is, and that itself we will be seeing some numericals related to this motion and plane, types of numericals which you can see, and the motion and plane. Okay, so there will be a single video for all the numericals through the projectile motion, uniform circular motion, and the vectors together, you can see it. Okay, and after that the motion and plane will be completed. So we will be starting the next chapter after this video, that is laws of motion. And I think this force and the laws of motion you have already learned in the 9th class also. It will be similar, but some few topics will come into the 11th class, because we have to read some more different from that of the middle class and the higher classes, right? So next we will be seeing the chapter 5, that is the laws of motion, in the next videos. Thank you class, and sorry for the disturbance throughout my voice also.